Hello. We're about to start. Unfortunately, there are only 3 students here. I've just sent you a link to a board. I'm going to share my screen with you today. But if it's more comfortable to use this link, please use it. So the problem was that on their videos, we don't have my notes all the time. Sometimes I just I have to highlight them manually, but sometimes I miss it, and so we don't have them on video. And about the video, I remember someone asked me about the availability of the video. The answer is yes, they will be on YouTube. I hope maybe the next week. Okay? So let's start our class. As usually, I ask you to turn on your cameras and microphones and tell us all your questions and comments. So let's start. I'm very glad to see you and to imagine those whom I cannot see now. So let's begin. Oh, such many people, such many new people. Okay. First of all, on Monday we've discussed some question concerning cosets, and let me give another comment on this question. So I'll share my screen with a board. Yeah, just here. Wait a minute, please. This is, well, okay. Do you see the board, guys?
Yes.
Nice. So you can see it by the link or on my screen, on my sharing screen. So first of all, let's discuss one question from our Monday Q&A. We proved on Monday that we have some group, some subgroup H in the group, the two cosets. Where are my notes? Oh, here. Okay. The two cosets are the same coset if and only if g to the minus first power h belongs to h. Yeah. And you asked me if it is true that such coset of element g and a coset of element of g inverse are the same. So let's apply this our effect to this case, and we'll gain that this is the case when g to the minus first power to the minus first power multiplied by g to h. But what is this element? It is g squared. So if and only if g squared belongs to h, so the cosets of g and its inverse element are the same. Okay? So let's start solving our problems for our today's class. Do you have the problems, the paper with them? It's on Wiki.
Yes.
Usually. So, first of all, let's discuss homomorphisms from different groups to some other groups. Let's discuss something like that. We'll not strictly go through the problems in this paper, but we'll discuss some questions that are very tightly connected with those problems in our paper and your homework. Okay, but sometimes I'll formulate the problems by myself and explain some useful things. So, first of all, let's discuss homomorphisms. Suppose we have two groups, G and H, and some mapping phi from G to H. So this map is a homomorphism when for every two elements of our group G, the operation looks like phi of G1, G1, G2 equals phi of G1, G2. Agree?
Mm-hmm.
So, G2. Okay. How can we find some homomorphisms from, for example, the group of integer numbers with addition to the group of all reminders modulo 6 with addition? How can we build all of the homomorphisms? Actually, we know that we can represent every element of our integers as 1 multiplied by this element. Yeah, that means that we take 1 and add 1 k times. Okay, so imagine I know the image of 1. Then how can we build the image of k? We take k and write that k equals 1 plus 1, etc. Knowing that we have a homomorphism, we can write down something like that. This is phi of 1 plus phi of 1 plus etc. plus phi of 1 k times, okay? So we see that knowing the image of 1, we know the image of every element in our group of integer numbers. Agree? So if you have questions, please ask them, okay? And in our case, what do we have to do? We need to find all the homomorphisms from our group of integer numbers to our group of reminders. Yeah. Let's say that the image of 1 equals, for example, 0 or 1 or something else in our group of modulo 6. Yeah. And knowing this, we'll know the whole homomorphism. Do you agree?
Mm-hmm.
How can I find the image of K? I'll write down something like that. This is K multiplied by the image of 1. And that's all. And this is a homomorphism from our group of integer numbers to our group of reminders. Yeah. Sometimes we have not additive group in the image here. Okay, here. But we have a multiplicative group. Yeah, let's imagine. In this case, we have to write down something like that in multiplicative case. The image of 1 to the kth power. Okay? Because the operation in the image is multiplication. Let's consider analogies. Where we can see some problems with this method. Let's consider the opposite case, where we have the group of reminders, and we need to find all the homomorphisms to real numbers. Let's act in the same way. Take some element which generates all our group of reminders. We agree that this additive group is generated by 1.
Yes.
Okay. And can I take, for example, 2 as a generator?
But it won't form the whole group.
You're right. 2 doesn't generate this group because to generate a subgroup consists of 2, 4, and 0, and that's all. But with 1, it's okay. So I take 1, and I say that the image of 1 equals, for example, 0. Is it okay? What homomorphism I gain in this way? Every element of our group of reminders, which is 1 multiplied by k, or 1 plus 1 plus 1, k times, goes to phi of 1 plus etc. plus phi of 1, which is also 0. And this is a homomorphism. That's okay, right? But if I take something like that, let's say, for example, that the image of 1 is the image of 1 is, for example, 3. Then I take 1 plus 1, the image is 6. And then 1 plus 1 plus 1, 6 times, which is 0 in our group, right? But using the previous rule, we have to write down that it is 3 plus 3, 6 times, okay? And this equals to 18 in our group of integers. And it's not 0. I have some.
Excuse me, I didn't get why. How did you construct the homomorphism from Z6 to Z?
Actually, I didn't do it. I'm trying to find homomorphisms, and I'm trying to do it in the previous way, okay? For example, I take some arbitrary image of the generator. knowing the image of generator, I know the whole homomorphism. Is it true? If I know the image of generator of our subcyclic group, I know the whole homomorphism. But maybe sometimes the image, even knowing the image, doesn't help me to construct the homomorphism. Maybe sometimes there are no homomorphisms, or there are no non-trivial homomorphisms. Okay, and this is the case here. I had to get 0 here because the image of 0 is also 0 when I consider homomorphism, right? The neutral element goes to a neutral element. And here I see that neutral element, the image of the neutral element is not neutral, okay? So here I have an arrow, not an equality sign, but an arrow. You see that I cannot construct non-trivial homomorphism. From reminders modulo 6, I cannot map the elements to integers because of some finite sums of elements in our group of reminders. Some finite sums are equal to 0. And here in the integers numbers, there are no non-zero numbers such that, for example, 3 here, such that k plus k many times equals to 0, where k is non-zero number. You see the problem? Let's discuss some questions. And what conclusion should I conclude from this point? Okay, who understands what is happening now with the homomorphisms from reminders to integers?
Not quite.
Not quite understand. Yeah. What's your question? Please ask a question.
Like, it's not really clear for me how to provide the homomorphism, like by definition. How do we prove that image exists there? I mean, I don't quite get it from your notes.
How can we prove that it doesn't exist?
No, that it exists.
We cannot prove that it exists because it doesn't exist. I showed you one of the homomorphism which actually exists when every element goes to 0. And this is a homomorphism. You agree with this point? Yeah?
Okay.
Okay, this is a 0 homomorphism. And everything is okay with this homomorphism. But here, let's imagine that I've chosen, excuse me, I've chosen some image of our generator. I've chosen the image of, wait a minute, please, of the generator, for example. The image of our generator equals some non-zero element, some non-zero integer element. What have I checked? Let's check that 1 plus 1 plus 1 6 times, which is 0 in our group of reminders. You see, you know that it's 0, goes to 0, but it goes to k plus k plus k n times, which is k times n, which is not 0, because this is 6. This is not n, actually. This is 6. k multiplied by 6 in integer numbers is non-zero when k is non-zero, and we took non-zero k. So we cannot build any non-zero homomorphism in this case, because here some non-trivial sums of elements are zeros, because their reminders are zero. And here, every non-zero sum is non-zero in the integers. So the only homomorphism I can build here, it's a zero homomorphism.
Okay.
Okay. So any questions concerning this point?
Can you please share the link of the board? Because I better see the whole picture of the solution. Or
Okay.
yeah,
I think that I shared it in the top of our chat. I'll copy it. Okay, where is our chat? Our chat is here, and here's the link.
thank you.
Okay, nice. So I'd like to okay. So let's solve another problem about homomorphisms. Let's find now homomorphisms from reminders modulo 4 to reminders modulo 6, and from Z6 to Z4. As in our previous case, when you considered integers and Z6. Here we consider Z4 and Z6, and we'll try to find homomorphisms from one to another. Okay, let's do it. Firstly, from Z4 to Z6. Let's take one here and try to find the images of one from Z4. We can map 1 to 0, and that will be zero homomorphism. Okay? Are you still with me, guys?
Yep.
Okay.
Yeah.
So do you agree that we can construct such kind of a homomorphism, zero homomorphism? We take one from Z4 and map it to 0. And the homomorphism is 0. It maps every element to 0. Such nice homomorphism. Then let's say that 1 goes to 1. So if we add 4 ones in our Z4, we'll have 0. Yes? So 1 times 4 equals 0. And excuse me, I have some problems with my tablet. Okay, so we'll have 0. What do we have if we multiply 1 by 4 in Z6? We'll gain 4 modulo 6, yeah? And it's not 0. So we cannot map 1 to 1. You see?
Mhm.
Do you see where it's the problem? Yeah.
Yes.
May I
That
ask a question? What is a zero homomorphism?
zero homomorphism. This is a homomorphism such that phi of x equals 0 for every x from our group. In our case, Z4. Zero homomorphism.
But any group homomorphed to by zero, like all groups can be homomorphed by zero.
You're right. We can construct zero homomorphism from every
For-
group to
Yeah,
every
yeah.
group.
So,
That's true.
but okay.
That's a trivial case, and we have to consider other cases. Okay, so can we map 1 to 2 and get a homomorphism? How do you think?
I think it's not surjective, right?
Why? But isn't
From
the
one,
homomorphism?
wait, from one.
Is this a homomorphism? Actually,
No,
why not?
because it doesn't map all the elements of Z6.
Because there is no mod for 4. Because if we got 2, we are going to get any, how's it called? So our mod gonna be 0, and it's not.
Okay, you're right. The reason is the same as in the previous case. We take 1 multiplied by 4. This is 0 in our group. And the image. What do we have for the image? 2 multiplied by 4, which is 2 modulo 6. And this is not 0 modulo 6. So this one and this one, we cannot construct such homomorphism. Okay, let's see what we have when we map 1 into 3. 1 goes to 3. What's about homomorphisms in this case?
It's gonna be same.
Actually,
Yep.
if I compute something like that, here I have to multiply 3, the image, by 4. And this is 12, and this is 0 modulo 6. This is 0 both modulo 4 and modulo 6.
Yeah.
Here we have 1 by 4, and here we have 3 by 4, yeah, for images. And this is 0, and this is not a problem. So you see, actually, the rule is the following. If we have some cyclic group, in the more general case, so not this one. So we have some cyclic group generated by 1 cyclic group with addition, and we have to construct a homomorphism into some other cyclic group, say that M. We have to map 1 to some K such that we'll have the following thing. multiplying k by this order n, we have to gain 0 modulo this order of a group. So if we construct such homomorphism for which this condition holds, we don't have problems with the images. So here we have 0 multiplying k by n, and here multiplying 1 by n, and here we have 0 multiplying the image of 1 by n. You see? Please ask questions if something is unclear. No questions?
I think it's clear.
Okay, nice. So my question is, please build all the homomorphisms from Z6 to Z4 and from Z4 to Z6 using this rule. How can we describe all the homomorphisms using our rule? Who can name all of them? Any volunteers?
I can try.
Do please.
Okay, if the first one is going to be 0, 2, 3, 2, 3. Oh no, it's not 3. 2, then 4, and
4 is 0, modulo 4.
yeah, 4 is 0.
And that's
So
okay.
that's all, yeah.
And here from Z4 to Z6?
Okay, so it's going to be 0, it's going to be 3, then 1 and 3.
0 and 3.
Yeah, no, 0 and 3, yeah.
That's all, you are absolutely right. Is it clear for all of the group? You have an opportunity to ask questions now. No questions. Okay, let's go on. A question? No?
Yeah, I have a question. Except 1, we don't have any other element from the first group to another one, right? And because I still quite don't understand from the definition, we have to construct a bijection from one group to another one.
Actually, they are not bijections. In the general case, we construct only homomorphisms. And concerning the previous point, why we show only images of 1? What about other elements of, for example, Z6? Yeah, this is your question.
Yeah.
Let's see. Let's see here. For example, for our this homomorphism, this one. What do we have for other elements? I know that Z4 consists of 2 elements, 0, 1, 2, 3. And every element of Z4 can be represented as 1 plus 1 plus 1 k times. Okay? This is 1 by k. Knowing that we construct a homomorphism, we can write down something like that. phi of k equals phi of 1 plus 1 plus 1 plus 1 equals phi of 1 plus phi of 1 plus phi of 1, the same
no.
number of times.
I got it. No, yeah.
Okay, so knowing the image of 1, we know the image of every element in our cyclic group.
Thank
Okay.
you. Yeah.
Nice. The next one. No other questions. Okay, let's consider direct products now. Let's consider the products. We have some problems concerning this topic. Where are they? Where are they? Oh, here. So, do you remember the definition of direct product? Who can remind us the definition?
Excuse me, can you repeat your question, please?
My question is, what is direct product? Do you remember it from the lecture?
Isn't it just all elements from the first group multiplied by the corresponding element from the another group?
So yeah, it consists of all the elements of Cartesian product of the sets.
Right. It's more precise than the previous answer. It is the set of all. This is the set of all. Let me write it down. Let me write it down here. Suppose I have two groups, not two, but n groups, G1, G sub n, and the direct product of these groups is a group consisting of all the elements of Cartesian product, which is a set of strings of length n, where every element belongs to its group. On the first place, there are elements of G1, on the second of G2, etc. And what is the operation in this group? We multiply two strings using the operation of every position. Remember now the definition. So how can we multiply? How can we multiply, for example, G1, Gn, and G hat 1, G hat n? We merely take the elements from the first positions and multiply them as in G1, then on every other position, and finally Gn to Gn hat, using the operation which is in our last group, Gn. Yeah, here every operation is the same as in G1 or G2 in the corresponding groups. Okay, is it clear? Okay, some questions? No questions. Okay.
Sorry, that means that we're gonna multiply every element with each element.
Every first element.
Every first. Okay.
Element, the second elements, and put them on the second position. Multiply third element and put them on the third position. And sometimes maybe we should add the fourth elements, because the operation in the fourth group is addition. So the operation is corresponding to the particular group here.
Okay.
Okay, let's consider some example. How can we? Excuse me.
Why did we multiply G1 by G2 hat?
because this is a definition of the operation in such kind of group. Let's consider some example and we'll see. For example, let's take the direct product of Z3 and S3. And let's multiply two elements. For example, 2, 1, 2, and 2, 1, 3. How should we multiply them? How should we apply the operation to them? On the first place, I have elements from our group Z3 with addition. So I add 2 and 2 modulo 3.
There's a typo, I guess, in the definition of the operation.
I didn't get your question.
There's a typo mistake
Where?
in the definition of the operation.
Where?
Like
don't
we got two tuples and we multiply G1 by G2 head, not by G1 head.
Oh, I see. Thank you. This is G1. Okay, thank you. Now it's correct.
Mhm.
Yeah. Okay, thanks. So here I add 2 and 2 in Z3. So this is 2 plus 2 modulo 3. And here I multiply 2 transpositions in S3. Okay? And I have 1. And what's the product of 1, 2 and 1, 3? Here I have 1, 2, 3, 3, 2, 3.
1, 3.
1, 3, 2. This
Two,
is a 3 cycle, yeah? 1, 3, 3, 2, 1, 1, 2, 2. So that's all. That's the product of these elements. Okay, so what should we find now? The problem number 10. We have two groups, and considering some arbitrary element of these two groups, we have to prove that the order of this element is the least common multiple of the orders. Do you remember the definition of order of an element? So let me ask this question in the following way. Here, when we constructed homomorphisms, what's the order of element 1 in group Z6?
Of which one element? Of which element?
Element 1 in group Z6.
1.
1.
Why 1?
Oh, no.
It's because it's the cardinality of generator of 1. So like the generator of 1 is 1 to power in the first power, in the second it's still 1. So the cardinality is also 1.
But it should.
Speaking about powers, we have to remember about.
Oh wait!
equation.
It's that without addition, but with addition. Oh, I see. Okay, then it's not 1, and we can find it directly. Z6. It's from 0 to 5. 1, 2, 3, 4. 1, 2, 3, 4.
Yeah, it's just 6.
It's 6.
Yes,
Why
it's 6. Yes, it's 6. I agree.
Yeah, order is the amount of elements of the group. Is it correct?
In our case, yeah. the order of the generator is the amount of the elements, because we have to add some ones to each other and find the minimal. For example, let it be m, and find minimal m such that this sum, let it be Sm, not Sm. It's, for example, let it be Cm. The minimal m such that Cm equals 0. So the sum of m elements is 0, the minimal amount of these elements in this sum. And what is the order of, say, 2 in Z6? What is the order of 2 in Z6?
3.
3, because we have to add 3 2's and we'll have 6, which is 0 modulo 6. Okay, then let's discuss the problem. We have two groups, G and H, and some element X from this direct product of these two groups, which is GH. And the order of X equals the least common multiple of two orders. Why is this the case? So okay, let's find out. First of all, let us multiply X such times X by X by X by X, this number of times. Let it be, for example, then n. I denoted the least common multiple as n. So I have G to the nth power. Say the operation is multiplication, and H to the nth power. Yeah. And now I know that n is a least common multiple of these two orders. So I can write down it like that. G to the, say, order G multiplied by n divided by order G. Because n is divisible by order. Yeah, and the same for H. H to the power order H multiplied by n divided by order H. Here we have that first, on the first place, we have G to order G. This is the neutral element of our group G to some order, which is also a neutral element. And here we have H to the order of H. This is the neutral element of the group H to some power. And this is the neutral element of G, the neutral element of H, which is a neutral element of our direct product. You see? Some questions about this speculation. Do you have any of them? No questions. So we see that the order of our element X is less than or equal to n. Okay, And knowing that x to some power, say it's m, equals to g to the mth power, h to the mth power. Knowing that this is the neutral element, we can also imply that m is divisible by the order of g, and m is divisible by the order of h. Is it clear? Guys, are you still here? Okay. So, what is the minimal number with this property? The minimal number is actually the least common multiple of our orders. Okay? So, what do we see here? If we know the orders of two elements of some groups, and we should find the order of the element of the following type in their direct product, we should only find the least common multiple of these two orders. Okay? But it's true only for direct products and some other cases. It's not the general fact about all two elements in their orders in every kind of group. So, since it's clear, let's find the order of some elements of such kind of direct product. This is a problem 11. Here we have a symmetric group of order 3 and Z4. And we consider the direct product of these two groups. And let's find, say, the order of the following element. The following elements: 1, 2, and 3 here, and 1, 2, 3, 1, 3, 2, 1, 3, 2, 2. So this is problem number 11. Let's try and find the orders. First of all, for the first element. Firstly, we have to find the order of 1, 2 in our group S3. What is the order of 1, 2? The order equals 2, because if I multiply 1, 2 by 1, 2 2 times, I'll get the neutral element of our symmetric group, right?
Yes.
Yes.
So, what is the order of 3 in Z4?
Order of 3 from Z4 in
S3.
Is it actually 3?
3 plus 3 is 6, modulo 2 is 2,
2.
modulo 4 is 2. 2 plus 3 is 5 modulo, it's 1, 2, 3, and 3 plus 3, it's 1, 0, 1, 2, 3, it's like 4.
4, it's 4, okay, it's 4, and here we have that the order of this element is
Their least common multiple, and it's 4.
It's 4, right? The next.
Excuse me, can you please repeat? What did you write there? I mean, what is this 1, 3, 2, and 2? Like, what is it for?
Okay, this is the 3 cycle. I'll write it
Mhm.
down here. 1, 3, 2 in S3 is the following permutation.
Oh,
I'll
I
write
know,
it
I know,
down
I
using-
know what it is. I mean, why do we have to write it? We did just compute the order of 1, 2, and of 3, and what is 1, 3, 2, and 2, 4 there?
I'd like you to consider some examples of different elements of this group. And this was an arbitrary choice.
Okay. Okay, I got you.
Okay, let's find the order of these elements.
Okay, order 1, 3, 2 multiplied by 1, 3, 2.
Do you remember the order of some cycles? The order of 2 cycle is 2.
Then the order of 3 cycles, 6, or no, it's not 6.
Yeah, it's still 6. Order of 2 cycles, 3 cycles is 6.
Because
Actually,
it should be 3 plural.
why it should be 3? Why should be the length of the cycle? Because look here, how many these cycles should I apply to some number to map it to itself? When I apply this cycle to, for example, one time, I see that 1 goes to 3. When I apply it the second time, I see that 3 goes to 4, or 3 goes to 2. And the third time, 2 goes to 1. So after 3 applications of this cycle, I gain that 1 goes to itself. And the same true about all the numbers in this cycle, okay? And the order consequently equals to the length of this cycle. And you may directly compute the third order of this cycle and see that this is a neutral element. So the order of this cycle equals 3. And the order of 2 in that work, what is it?
Two maybe?
2.
2.
This is 2 because 2 plus 2 is 0 modulo 4. So what is the order of whole our element?
It's 6.
6.
It's 6 because the least common multiple equals the product in our case. Okay.
Excuse me, could you please explain why is the order of permutation 1, 2 is equal to 2?
You may directly multiply.
I don't get how the operation.
The operation is the same than in our symmetry group. So how can we multiply 1? I write down 1 here. How can we multiply cycles? 1 here, 1 goes to 2. Then I go here and see that 2 goes to 1. So 1 goes to 1. Then 2 goes to 1 in this cycle. Then 1 goes to 2 here. So 2 goes to 2. And this is a neutral element. Every element goes to itself. Is it clear?
That seems strange for me. Okay,
Do you understand the cyclic representation of a permutation? I mean that...
I will try to figure it out by myself.
Okay, look here, please. You should understand that the cyclic representation of this particular permutation written down in 2 rows is 2 cycle. So this is the key point. Okay. So you may also remember that the order of a cycle equals to the length of this cycle. Actually, I showed why this is the case. Okay, do you have any questions concerning the direct products and the way to find the order of an element of our product? No questions?
No,
It's
no.
pretty clear.
The next question is the following. Do you remember the Chinese remainder theorem? And why sometimes this kind of group, cyclic group of order Mn, is isomorphic to the product, the direct product of Zm plus Zm, or how to build homomorphisms and the inverse homomorphisms from the lecture. Do you remember something like that? That we can take element k here and map it into such element, where these two k's are modulo m and modulo n.
Is K subgroup or what?
K is an element.
Element, okay.
Not a subgroup, but this is an element, some arbitrary element of our group. Okay, so let's consider some examples. For example, let's see what do we have in the following case, where Zmn is Z6, and we have the product of Z2 and Z3. How can we build a homomorphism from this group to this product, or from this group to one of these guys? We've done it already at the beginning.
Well, just by computing each product, like the LCM of both of them. No.
Okay, that's the same. So I take one here and map it into some, for example, QL. Okay, and I know the whole image, all the images of elements in Z6. But actually, I have to check that the orders of these elements Q and L are that for the orders I have 6 times Q equals 0 modulo 2, yeah, and 6 by L equals 0 modulo 3, yeah. So that the order of our element here is a divisor of of the image here. And if I mapped one to this kind of element, I also know the images of every elements here. So I know that that's KQ and KL. L. Right?
Mhm.
Okay, so we know it already. So let's consider the following homomorphism. Let's map 1, 2, 1, 1.
Mhm.
This one is 1 modulo 2, this one is 1 modulo 3. Why I can construct their homomorphism actually? Because here I multiply 1 by 6 and get 0. And here I multiply 1 by some divisor of 6. These two orders of this group are the divisors of this one, because I consider only such cases where the product of these orders is the order of our big group. Okay, so everything is okay if I map 1 to 1, 1, and then I map k to kk, k modulo 2, k modulo 3, right? So it's actually a homomorphism. Then I ask myself a question. Is this homomorphism bijective? Is it a isomorphism? How can I check? How can I check it? I should build the inverse homomorphism for this kind of homomorphisms. Yes?
Mhm.
So how can we act in this particular case? When k, every k from Z6 goes to k modulo 2, k modulo 3. How can I find the inverse elements?
We have to take the same elements from the 3 and 2 from the groups.
More explicitly, please.
So
Elements.
maybe we have to take same elements from the group 2 and 3 and then mod them on 6.
Okay, let's take, for example, 1.
Mm.
So actually, we have to find such an element from our group Z6, such that the reminders are as we need, as we want. So is it true that if I find the elements which go to 1, 0 and 0, 1, this one is modulo 2 and this one is modulo 3, I find all the let it be phi, and I need phi to the minus first power from our direct product to our group Z6. If I find phi to the minus first power for these two elements, is it true that I find the whole inverse mapping? It's true, because every element, for example, QL, can be represented as Q multiplied by 1, 0 plus L times 0, 1, where Q and L are integers. So this multiplication is addition of Q elements 1, 0. Okay, and how can I find such an element that its remainder modulo 2 is 1 and its remainder modulo 3 is 0. What is this element of Z6? Every k goes to its reminders, modulo 2 and modulo 3. So the inverse image is such an element k that its remainder modulo 2 is 1 and its remainder modulo 3 is 0. For example, this is 3, because 3 goes to 3 modulo 1, which is 1, 3 modulo 3, which is 0. Do you agree?
But for yeah.
Okay. And what's about 0, 1?
It's 4.
It's 4 because 4 goes to 0 modulo 2, 1 modulo 3. So for this mapping phi, the inverse mapping is the following. It maps 1, 0 to 3 and 0, 1 to 4. In the general case, how can I find these two elements, 3 and 4? We know that according to the Chinese remainder theorem, if these two elements, 2 and 3, are coprime, that for every set of reminders, in my case, the first set of reminders is 1, 0. For every set of reminders, there exists such an element, such that the reminders are as I need. So, in our case, these guys are coprime, 2 and 3. And I can find such an element, 3, that its reminders modulo these two elements, 2 and 3, are the following, 1, 0. And using the Chinese remainder theorem, the algorithm from this theorem, we can find these elements 3 and 4 in the general case. Questions? No questions. So let me make some conclusion here. Is it true that Z6 is isomorphic to Z2 direct product Z3?
Yes.
Why?
Because we find because we find the elements which are isomorphic there.
Yes, we constructed their isomorphism. We constructed their homomorphism phi, which moves k to this string of reminders. Yes, and this is homomorphism. We already know it, and this homomorphism is bijective because we've already found their inverse homomorphism, which works like that. So we found inverse images of elements 1, 0 and 0, 1. And every element in our direct product can be represented using these two guys. Okay, these two elements, 1, 0 and 0, 1. And this map is also a homomorphism, so we constructed bijective homomorphism. This is isomorphism. Okay. And the last point of our today's class is about classification of different abelian groups. I suppose it's about the 15th problem in our list of problems. Yes. So, do you remember two types of two ways to represent groups of abelian groups of some finite order? First of all, if we have some modulo, say 36, and I know that G is a group of orders 36 and G is abelian or commutative if you prefer. And I would like to represent all the groups with these properties. First of all, I can write down that 36 is 2 to the second power 3 squared, right? So all the groups can be represented in the following way. Z2 multiplied by Z2 by Z3 by Z3 and some others. For example, Z4 by Z3 by Z3. What do I write down? I write down the different combinations of the following type. ZP1 to the K1 power, etc. That Pn to the Kn power, where P is prime. And some P can be more than one time here in these indices of these groups. Do you remember such kind of notation? That was, if I'm not mistaken, claim 53 in the lecture notes. Let me have a look. Let me have a look here, here, here. Claim 53, something like 51, 53. Okay, here. Do you see the second point? And the next type of representation is here, where the orders of the groups are, where the previous order divides the next order. Do you remember this claim and this result?
Yes.
Okay, thank you. Then let's solve the last problem of our today's class. Let's check if their groups that 6 times that 36 and that 12 times that 18 are isomorphic. We can use one of those decompositions. First of all, let's decompose this group. We already know that it is that 2 times that 3. Yeah? And here, what are the primes? 36 is 2 squared by 3 squared. So this is a product of that 4, that 9. And we cannot decompose.
But actually, we not have to decompose all the groups. We just can decompose, for example, 36 and 12.
Okay, let's decompose. Can tell me what is the decomposition here?
So it's Z3 and Z4.
Z3, Z4, and
That's 18.
Z18, Z18. And what do we see here? Here, Z3 here, Z4 here. And is it true that Z2 direct product Z9 is isomorphic to Z18? Is it true?
I don't know.
Okay,
I hope so, but
can we decompose Z18?
it could be that's it could be Z3 multiply Z3 and
Actually, this is Z2 direct
okay.
product Z9. And we see that the decompositions are the same. And let's discuss why Z18 is isomorphic to Z2 direct product Z9. Using the same fact, the same Chinese decomposition, Chinese remainder theorem, we can construct the homomorphism from here to here, and the inverse homomorphism from here to here, because 2 and 9 are co-prime. You see? So
yes.
the key property here is that 2 and 9 are co-prime. And let's discuss why Z9 does not isomorphic to Z3 direct product Z3. So first of all, we can't apply Chinese remainder theorem here because these numbers are not co-prime.
Yes.
Okay, but we can prove the isomorphism. That doesn't mean that there are no isomorphism. So how can we prove that there is no any isomorphism? Since these two groups are isomorphic, here there exists an element X such as the order of this element equals 9. For example, 1. The order of 1 in our group is 9, or in Z9. Yeah? And are there any elements of order 9 here in Z3 times Z3?
It's going to be 0.
0 has order 1. Because 0 plus 0, 0 one time is already 0. How can we find the orders of these elements? The order of element AB from our direct product is the least common multiple of orders of A and B. What are
it's 9.
here? 0 and
It's 3. It's 3. It's 3.
1 and 3, and here 1 and 3. So the least common multiple is 3. For
3.
every element, we know the order. The order is 3. But here there are some elements of order 9. For example, 1. So these two groups are not isomorphic.
May I ask you a question?
Surely.
If orders are equal, this means that groups are isomorphic.
Not yet.
Not yet. Okay.
Not yet. But since the orders are not equal, the set of orders of elements, the groups consequently are not isomorphic. So that was the last question of our today's class. If you have any questions now, please ask them. Or we'll discuss questions on our Monday's Q&A.
So, for example, I'm going to ask you about Z2 multiplied Z9 and isomorphic to Z18. So if we will say that 2 and 9 are coprimes, that means that they are isomorphic to Z18. Is it right?
Yeah. Yes.
Okay.
No, in the general case, if we have Zm and Zn, and we know that M and N are co-prime.
Mm-hmm.
So it means that the direct product is isomorphic to that
Of their product. Ah, okay.
Yeah.
Thank you.
It's true. It's true according the Chinese remainder theorem and the claim 53 in the
It's always holds true. Or there is some, like for example,
if
special.
we consider cyclic groups of order n and m, and the orders are co-prime,
Mm-hmm.
it's always true.
Okay.
Okay. Some else? No questions. So,
Is it possible, excuse me,
okay.
is it possible if like the decomposition contains the sets, for example, Z2 and Z4, and they're isomorphic to Z8?
The same speculation as for Z3 plus Z3 shows us that here in the two direct product Z4, there are no elements of order 8. And there are such elements in that H. So using the orders, we can prove that these two guys are not isomorphic.
So we can only use the Chinese remainder theorem then, right?
Yeah. And here you see that if you take the element of order M here and the element of order N here, and the string from the direct product, the order of this element will be the least common multiple, and the least common multiple is the product of these two elements since they are co-prime. So here we have an element of order Mn, and here we have an element of order Nm. So this does not prevent us from proving their isomorphism.
Mm-hmm.
Okay. Mm-hmm. Okay.
And
Some else questions?
Okay.
No questions. Okay. Thank you for the class. See you on Monday.
Thank you.
And okay. Goodbye. Good luck.
Goodbye.
Bye.
Thank you.
Oh, excuse me. May I ask
Yep.
one last
Mhm.
question?
Okay.
Is it possible to reschedule the classes?
Schedule the classes and schedule.
The seminar classes.
What do you mean by schedule?
Reschedule. Ну, в общем, это на другой день поставить.
Reschedule.
К вам обращались?
Новые семинары? I'm not sure. I'm not sure. What's the reason?
Ну, вот, в принципе, возможно ли это или нет? Если да,
Не знаю, нужно узнавать в учебном офисе.
то есть в учебный офис обращаться касательно этого вопроса.
Да. Единственное, мы можем переставить консультацию.
Ну, вот по поводу консультации совсем нет вопросов, а четверг довольно-таки нагруженный день, и это последняя
Консультация,
пара.
она по-прежнему в понедельник.
Понедельник, да. Это нормально в понедельник?
Да,
Да-да-да. Перенести, потому что у нас сегодня еще у нас сегодня матан и
да, у нас
две пары
шесть.
по алгосам, и к 4 часам уже голова не очень хорошо работает.
Я вас поняла. Смотрите, обсудите это внутри группы и обратитесь в учебный офис, поставьте меня, пожалуйста, в копию. В принципе, я готова, у меня есть еще свободное время для этого, но как бы это надо сделать централизованно. Из-за расписания отвечает учебный офис. Вот. Только, пожалуйста, со всей группой это обсудите, чтобы это всем было удобно.
Да, мы на самом деле уже обсуждали в группе и опрос сделали. Вот.
Окей, тогда обращайтесь в учебный офис, ставьте меня в копию и решим. Не проблема.
Хорошо, спасибо, до свидания.
Не за что. До свидания. Goodbye. Всем успехов.
До свидания.